Ionic compounds in a nutshell. We're going to talk about ionic compounds, some features, some nomenclature, which is basically how do you name them, like formulas and all that stuff for it. So what happens to ions in water? So you have two ions, and if they're oppositely charged and there's an attraction between them, you have what's called an ionic compound. An ionic bond forms between the two ions, and then you create an ionic compound out of it. Force of attraction between ions are called electrostatic attractions. A fancy way of saying that opposites attract. So when you have a positive and negative ion near each other, they attract each other, and that attraction is called electrostatic attraction. Number of each ion and compound depends on number needed to give an overall charge of 0. So, for example, let's say we have sodium ion. Let's say we have oxide ion. Now, when these two come together to form a compound, you can't produce just NaO. The reason is because positive 1 and negative 2 gives you an overall charge of negative 1. That's not what you want. What you want instead is that the compound has a charge of 0. So how do you accomplish that? Well, if you have two NAs and one O, now instead of having a positive 1 charge coming from an A, you have positive 2. And for oxygen, the charge is negative 2, so your overall charge is 0. That's what you're shooting for. And to make an ionic compound, your charge has to add up to 0. So keep that in mind as you're doing them. So here's an example. We have beryllium with 2 valence electron, fluoride with 7. Now fluoride wants to have 8. Beryllium, remember, is one of those exceptions that only wants to have 2. So what beryllium is going to do when it collides with fluorine is to lose both electrons. So when you lose both, you get a positive 2 charge. Let's say fluorine takes one of them. Now fluoride's a negative 1. Now look at the attraction between them. So they're going to attract each other, but you notice the overall charge right now is not 0. The overall charge right now is going to be a positive 1, right? Positive 2 minus 1 gives you a positive 1 charge. That's not what we're shooting for. So what you're going to need is actually a second fluoride. And now you have overall charge of 0. So when you're making these compounds, you got to make sure your charge adds to 0. And I'm going to show you a shortcut for that. All right, here's aluminum. Here's chloride. Same logic. Notice 1-to-1 ratio doesn't work, right? Right now you have a positive 2 overall charge. What about second chloride? You bring a second in, now it's a positive 1 charge overall, right? Positive 3 minus 2, still not going to work. What you need instead is 3. So to write the formula for this would be just AlCl3. 1 aluminum, 3 chloride. So that's the way we write formulas, is by putting the ratio of each element in the compound. So here there's 1 aluminum. You don't put 1 as a subscript ever. And 3 chlorides. And there's your formula, AlCl3. Also known as aluminum chloride. All right, method of writing correct formulas for ionic compounds as follows. To determine the charge of the ions involved. And 2, crisscross the numbers. Really simple. 3, reduce values if they are divisible by each other. And I'll show you what that looks like in a second. So here's a crisscross method. Basically, the charge of one ion becomes a subscript for the other in the formula, and vice versa. The only requirement of this method is that you got to make sure that the subscripts are the lowest possible multiple of each other. I'll show you what that looks like. So, for example, this one, to crisscross, we bring the 4 down here, the 2 over here, so we get Pb2O4. Notice I didn't bring the charges, just the numbers down. That's what you crisscross. This is not the lowest possible multiple. This and this can be divided by 2. So what you have to ask yourself after you crisscross, can I divide the two numbers by one of them? And here you can. You can divide both by 2. So here's your actual formula. What if you wrote Pb2O4? You'd be wrong. Here's why. If you write 2 Pb's, and each of them are positive 4, right? And you write 4 O's, the charge is 0 overall. But you could also accomplish this by just doing 1 Pb and 2 O's. And this is the preferred structure. So technically this is 0, yes, but remember the rule for this method, unless you want to make it more complicated for yourself to find a different method, is to reduce it down whenever possible. And if the numbers are identical, if it's positive 2, negative 2, it's 1-to-1 ratio. So for example, if I have CO positive 3 and P negative 3, the answer becomes COP. So whenever there's the same charge, opposite in sign, 1-to-1 ratio, call it a day. Let's look at some examples of it. Magnesium chloride, magnesium is a positive 2 because it's group 2A. Remember, everything from the left side of the periodic table is a cation, and magnesium is group 2A, so it's positive 2. Chloride is group 7A, so it's a negative 1. So that's where I got the charges from the periodic table. Crisscross, can divide, can reduce, so you're done. Tin 4 sulfide. First thing you want to do is write the charges. Please make it a habit to write the charges first. Don't try to shortcut it in your head. If you just do that extra step, you're going to avoid all the possible mistakes. So put the numbers. 4 because it's a positive 4 because the Roman numeral is 4. Sulfide is group 6A, so it's negative 2. Crisscross, get SN2S4. Now you know you can see you can divide both of those by 2, and you will. You get SNS2. So that's how this works. All right, moving on. Iron 2 oxide. Iron's a positive 2, oxide's a negative 2. Same charge, so it's going to be 1-to-1 ratio FeO. Very ugly compound. And when the charge is the same, just make sure you just reduce it down. All right, beryllium phosphate. So phosphate is one of the polyatomic ions, and that's going to be a little bit more complicated. So when you write the charges, you got to write the subscript as part of the formula. This is PO4 is phosphate. If I make this PO3, this is phosphite. The point is, if you change this number, you change the identity. So you can't touch the number. Just leave it alone. Don't do anything to it. The problem is that when I crisscross, the first thing you're probably thinking, does this make this BPO2? Does this make this BEPO8? What do? Don't get cute with the math. When you crisscross with a polyatomic ion, you need to put a number. When there's more than one of them, as a result of the crisscross, all you need to do is put parentheses around it. So parentheses around PO4. And notice I still brought the 2 over, just like I would expect to be. And all I'm doing is, at this point, putting the 2 at the outside of the parentheses indicate there's 2 PO4s. So that's what you do with polyatomic ions. You put them around in parentheses when there's more than one of them, and put the number on the outside, and you're done. The 3 still carries like you usually do. So that's a little tricky part to it, if you will, is that when you're dealing with these kind of compounds that have polyatomic ions, you do need parentheses at times. So anytime you need more than one polyatomic ion, you put parentheses around it. Now, please don't do this. If Na and NO3 is, let's say, the question, please don't do this. Don't put parentheses when you don't need it. The only thing you do is when the number is more than 1. So when the charge of the cation is 2 or more, parentheses. When it's not, don't. Don't put parentheses just for the sake of parentheses. You're going to make mistakes. All right, forming tips. Always determine the group the metals in first. Since that could tell you the charge, so group 1A is positive 1, 2A is positive 2, 3A is positive 3. Polyatomic ions, the way you could tell they're involved is the name of the chemical they're giving you has an ate or ite in it somewhere. If you say ate or ite is the ending, polyatomic ion, and since you're going to have to memorize these shouldn't be a problem for you to recognize, but just in case, if you want to be reminded, look for ate and ite. If you see ate and ite, the polyatomic ion involved. Place parentheses around the polyatomic ions when you have more than one of them in the formula. An ending of compounds with only 2 elements, always IDE. So anything you have any ionic compound, the ending is IDE unless there's a polyatomic ion. What happens if there's a polyatomic ion involved? This can be ate and ite as the ending of the name. So there's your options. You have 3 options. Either you have ide, which is the predominant one, ITE, which is if a polyatomic ion is involved, or AT, if a polyatomic ion is involved. All right, so let's try the first one, sodium oxide. So what do I do first? I'm going to sit there and write the charges out. So Na plus, oxygen is negative 2, cross. Na2O. Notice I didn't write the 1 because you assume it. You never put a 1. You just assume it's there. Beryllium sulfide. First thing I'm going to do is look where beryllium is. Group 2A, positive 2. Sulfide, negative 2 because group 6A. Same charge. So have a nice day. BS. Don't overanalyze. Aluminum nitride. Aluminum is a positive 3. Nitride is a negative 3. Same charge. Have a nice day. You're done. That's all you got to do. Just make it simple for yourself. Gallium, group 3A, so it's positive 3. sulfide, group 6A, negative 2, crisscross. 3 goes here, 2 goes there, so Ga2S3. And all these, the compound's overall charge is 0, just what we expect it to be. Strontium, group 2A, it's going to be positive 2. Iodide, group 7A, negative 1, crisscross, SRI2. Here's some more matching versions. MgS. Let's do it this way. We're going to look at these names and match it to the compound. Magnesium sulfite as a polyatomic ion. That's MgSO3. Magnesium sulfate. That's SO4. That's why it's important to memorize your polyatomic ions. It's here. Magnesium sulfide here. Here, calcium chlorate. Which one of these is chlorate? This one. Calcium chlorite, which one's chlorite? This one. And calcium hypochlorite, which one's that? That one. That's why it's important to know your polyatomic ions. It'll save you a headache. Moving on. Now we're going to do these. Calcium nitrate. Calcium's 2 plus. Nitrate, polyatomic ion, NO3, minus 1. Crisscross. Notice I got to bring a 2, so I need parentheses. So Ca, NO3 with a 2 on the outside. Next one, iron. You notice the first thing I do in all of these is figure out the charges. Roman numeral 2, so positive 2. Hydroxide's negative 1. Crisscross. Fe, I need to put a 2, so I'm going to put parentheses, because that's the way to do it. Aluminum carbonate, aluminum group 3A, positive 3. Carbonate, CO3, 2 minus. Crisscross, Al2. CO3, I got to put a number on the outside. It's not 1, so parentheses, CO3 with a 3 on the outside. Copper 2 phosphite. Copper is positive 2 because Roman numeral 2. Phosphites, PO3, negative 3. Crisscross, Cu3. PO3, you got to put parentheses because you have more than one of them. 2. And the last one, lithium phosphate. Lithium's positive 1 for group 1A. Phosphate's PO4, negative 3. Crisscross, Li3, PO4. There you have it. So all you got to do is just crisscross, and when there's a polyatomic ion involved, make sure you put a parentheses in order to deal with that. All right, key questions, a couple of them for you to try. Write formulas for the following. So we're going to do the same thing we did a second ago. Strontium, Sr, 2 plus. Nitrate, NO3, minus 1. Crisscross, there's a 2 here, so parentheses is going to be needed. Notice the charge, negative 2, positive 2, 0 overall, which we expect it to be. Iron 2, Fe2 plus, F minus 1. Crisscross, Fe, F2 don't need parentheses because there's no polyatomic ion. Please don't make the mistake of putting parentheses after everything. Magnesium, Mg, positive 2. Hydroxide, negative 1. Crisscross, Mg, OH, 2. Parentheses, why? Because once again, you have a polyatomic ion, you have a 2 you're carrying, so you got to put parentheses. 2 or greater, you need parentheses. Lead 4, Pb4 plus, O2 negative, crisscross, Pb2O4. First time in a long time that you had numbers being divisible. So 1, 2, so PbO2. And that's how you do these.